Welcome, and thank you for being here, in this quiet moment where the world outside can wait, and where nothing is asked of you except to simply rest, to breathe, and to let your mind wander gently upward, toward the sky, toward the clouds, toward those soft and ancient travelers that have been drifting above us since long before we arrived, and will continue drifting long after we've gone, indifferent to our worries, untouched by our hurries, moving at their own pace through the vast and patient atmosphere that holds them. Tonight, we're going to look up together, not with the urgency of those who seek answers, but with the gentle curiosity of those who simply want to notice, to observe, to let the sky reveal itself in its own time, and perhaps, in doing so, to feel a little lighter ourselves, a little more at ease, knowing that above us, always, there is movement and stillness both. There is change that happens so slowly it feels like stillness, and stillness that is in fact the slowest kind of change. The sky is never truly still, though it often appears that way, and the clouds within it are never truly fixed, though they sometimes seem to hover in place, suspended like thoughts we can't quite let go of, like memories that linger at the edge of sleep, and perhaps that's why we find them so calming, so endlessly watchable, because they mirror something in us. Something that wants to drift, to dissolve, to transform without effort or intention, to simply be carried along by forces we don't have to understand or control. When you look at a cloud, you're looking at something that weighs almost nothing, and yet can weigh 1,000,000 pounds. You're looking at something that seems solid from a distance, but would slip through your fingers like the coolest mist if you could reach it. You're looking at water that has forgotten, temporarily, how to fall, water that has found a way to float, to gather itself into shapes that have no names, no purposes, no destinations, only the slow and inevitable pull of physics, of temperature, of invisible currents that guide without grasping, that move without pushing. Every cloud is made of millions upon millions of tiny water droplets, each one so small that it would take 1 billion of them to fill a single teaspoon, and each droplet forms around an even tinier particle, a speck of dust perhaps, or a grain of salt carried up from the ocean, or a fragment of pollen, or even a microscopic piece of a meteorite that burned up in the atmosphere decades ago, centuries ago, eons ago, and these particles, these invisible seeds, float through the air until they meet water vapor, and the vapor clings to them, condenses around them, and slowly, particle by particle, droplet by droplet, something that was invisible becomes visible, something that was scattered becomes gathered, and a cloud begins to form. This happens not through any intention, not through any design, but simply because the conditions are right, because the air has cooled just enough, because there is moisture enough, because the world is at that moment in that particular column of air, perfectly balanced between being and not being, between invisible and visible, and the cloud appears, not born exactly, but accumulated, assembled from pieces so small that each one alone would be nothing, would be unnoticeable. But together, in their billions and trillions, they become something we can see from miles away, something we can point to and say, there is a cloud. And once formed, the cloud does not stay the same, cannot stay the same, because the air around it is always moving, always shifting, because temperature changes from one moment to the next, from one altitude to another, because new droplets are always forming at the edges, while old droplets are always evaporating, always returning to invisibility. And so the cloud is constantly making and unmaking itself, constantly arriving and departing at the same time. And if you watch long enough, you'll see it change shape, see it stretch or compress, see it brighten or fade. And you might think the cloud is moving, traveling from one place to another, but really, it's more accurate to say that the cloud is happening, is occurring in this moment, and this moment, and this moment. Each moment slightly different from the last. The ancient Greeks believed that clouds were made of thick air that had become dense and heavy, and while they were wrong about the mechanism, there was something poetically true in their observation, because clouds do exist in that liminal space between substances, between liquid and gas, between weight and weightlessness, between here and not here. And to watch them is to watch transformation itself, to watch matter forgetting what it was and becoming something else, then forgetting that too and becoming something else again, in an endless cycle that requires nothing from us, not our attention, not our understanding, only our presence, only our willingness to look up and notice. In the daytime, clouds are white or grey, and we tend to think of those as their natural colours, their only colours, but really, clouds have no colour at all. They are simply water, simply droplets suspended in air, and what we see is light, is sunlight scattering off those droplets in every direction, bouncing and rebounding and eventually reaching our eyes. And the white we see is actually all the colours of the spectrum combined, mixed together so thoroughly that they lose their individual identities and become something that feels like purity, like blankness, like a canvas that holds every possibility. The grey of a cloud is simply shadow, simply the absence of light that has been blocked by other droplets, by the thickness of the cloud itself, because when a cloud grows deep enough, dense enough, when there are enough droplets stacked upon droplets, the light from above cannot penetrate all the way through, and the bottom of the cloud darkens, and we on the ground look up and see grey, see the cloud's own shadow cast upon itself, and in this way a cloud can be both illuminated and shadowing at once, both bright and dark depending on where you stand, where you look, what angle the sun takes as it moves across its own slow arc. At sunrise and sunset, clouds become something else entirely. They become canvases for colour, for the reds and oranges and pinks and purples that fill the sky when the sun is low, when its light must travel through more atmosphere to reach us, must pass through miles and miles of air, and in that passage, the shorter wavelengths of light, the blues and greens, are scattered away, are dispersed and lost, and only the longer wavelengths remain. Only the warm colours, the fire colours, and these paint the clouds from below, from the side, turning them into something that seems almost unnatural, almost impossible, glowing like embers, like the world itself is burning slowly and beautifully at the edges of day. These colours last only minutes, sometimes only seconds, because the angle changes so quickly, because the sun does not pause in its setting or its rising. And by the time you've truly noticed the colour, truly taken it in, it's already shifting, already fading, already becoming something else. And perhaps that's part of what makes it so beautiful, so precious, the fact that it cannot be held, cannot be kept, can only be witnessed in the moment of its occurrence and then released, let go, allowed to pass into memory or into nothing at all. And then night comes, and we tend to think that clouds disappear with the darkness, that they cease to exist when we can no longer see them, but of course they're still there, still forming and dissolving, still drifting through the dark sky, invisible now to us but present nonetheless. And if there's a moon, especially a full moon, you might see them as shadows against the lighter sky, as shapes that block the stars, as movements in the darkness that remind you that the world continues its processes whether we witness them or not, whether we're awake or asleep, whether we remember or forget. There are clouds so high that airplanes fly beneath them, clouds that form in regions of the atmosphere where the air is thin and cold and impossibly distant from the ground. And these clouds, called noctilucent clouds, night-shining clouds, appear only in the deep twilight after sunset or before sunrise, when the sun has already dropped below the horizon for those of us on the surface, but is still illuminating the very highest reaches of the sky, still touching these clouds that float at the edge of space, 50 miles up, where the atmosphere barely exists, where there's almost nothing at all, and yet there's just enough water vapor, just enough meteoric dust from space, just enough cold for clouds to form. These noctilucent clouds are made of ice crystals coating particles of smoke from meteors that burned up as they entered Earth's atmosphere, and they glow with an electric blue color in the twilight, a color so ethereal it seems like something from another world, and in a way it is, because these clouds exist at the boundary between Earth and space, at the place where our planet's breath finally gives out and the vacuum begins, and to see them is to see something rare and delicate, something that only happens in summer at high latitudes, when the conditions are just so, when everything aligns in a way that cannot be predicted or controlled, only noticed, only appreciated when it occurs. But most clouds, the clouds we see every day, form much lower, in the troposphere, in the layer of atmosphere where all our weather happens, where we live and breathe and move through our days. And even these ordinary clouds, these everyday clouds, exist in a kind of taxonomy, a classification system developed over 2 centuries ago by an English chemist named Luke Howard, who looked at the chaos of the sky and saw patterns, saw types, saw families of forms that repeated themselves with enough consistency that they could be named, could be recognized, could be understood as variations on a theme. Howard gave clouds Latin names not to make them seem more complicated or more scientific, but because Latin was, in his time, the language of scholarship, the language that transcended borders and allowed knowledge to be shared across nations, across cultures, and his names were simple, were descriptive, were based on appearance rather than mechanism, and they persist to this day, largely unchanged, still useful, still accurate enough for both scientists and sky watchers, for meteorologists and poets alike. He named the puffy, heaped clouds cumulus, which means heap or pile in Latin, and these are the clouds that children draw, the classic clouds, the ones that look like cotton balls or sheep or whatever your imagination suggests, white and round and separate from each other, drifting across blue skies on pleasant afternoons, each one a small world unto itself, floating independent and free, and cumulus clouds form when warm air rises from the ground, carrying moisture with it. And as it rises, it cools, and the moisture condenses, and the cloud appears. And if the conditions are right, if there's enough instability in the atmosphere, these small cumulus clouds can grow taller, can develop into larger formations, can tower upward for miles, but on calm days they simply drift and slowly dissipate, their edges constantly evaporating back into invisible vapor, even as their centers continue to form and reform. Straight as clouds, Howard observed, were the opposite of cumulus, not heaped but layered, not vertical but horizontal, spreading across the sky like a blanket, like fog that has lifted off the ground but hasn't dissipated entirely. And the word stratus means layer, means spread out. And these clouds form when stable air is gradually lifted, when there's no convection, no rising thermals, just a gentle, even ascent that produces a gentle, even cloud, grey and uniform, the kind of cloud that can cover the entire sky, that turns the world diffuse and soft, that creates a light without shadows, a day without definition. And some people find this depressing, find it heavy or oppressive, but others find it peaceful, find it restful, this removal of harshness, this gentling of contrast. Cirrus clouds are the highest of the common clouds, thin and wispy, made not of water droplets but of ice crystals, because at the altitude where they form, usually above 20,000 feet, it's too cold for liquid water to exist, and so the moisture that reaches those heights freezes immediately, forms into tiny hexagonal crystals that catch the light and create those delicate feathered streaks across the sky. And the word cirrus means curl or fringe, and that's exactly what these clouds look like the curled edge of a piece of paper, like the fringe of a shawl, like brush strokes made with the finest brush on the biggest canvas imaginable. Cirrus clouds often indicate that weather is changing, that a storm system might be approaching, because they form at the leading edge of warm fronts, where warm air is gradually overrunning cooler air, rising up and over it in a slow-motion cascade that can extend for hundreds of miles ahead of the actual rain or snow. And so when you see cirrus clouds appearing in an otherwise clear sky, thickening and lowering over the course of hours or days, you're seeing the future arriving, seeing tomorrow's weather announcing itself in the most gentle way possible, giving you time to notice, to prepare, or simply to acknowledge that change is coming, as it always is, as it always does. And then there are combinations, clouds that partake of more than one type, that blend characteristics, that show the infinite variability that's possible within a finite set of rules. And so we have stratocumulus, which are layered clouds with some heap-like elements. We have cirrostratus, which are high, thin layers of ice crystal clouds. We have altocumulus and altostratus, which exist at middle altitudes. And we have cumulonimbus, the towering giants of the cloud world, The storm clouds, the clouds that can grow so tall they punch through the troposphere into the stratosphere above, the clouds that create thunder and lightning and hail and sometimes tornadoes, though even these, even the most dramatic and powerful clouds, start from the same simple principle: warm air rising, moisture condensing, droplets forming, one added to another, until the accumulation becomes visible, becomes massive, becomes capable of releasing energy that lights up the sky and shakes the ground. But tonight, we're not concerned with storms, with drama, with the fierce and the urgent. Tonight we're focused on the gentle, on the everyday, on the clouds that drift and fade without fanfare, without demanding anything. And these clouds, the quiet ones, are everywhere, are always present in some form, even on days we call clear. Because if you look carefully, especially near the horizon, you'll almost always see some faint wisp, some distant formation, some reminder that the air is never truly empty, never truly transparent, is always holding something, always carrying something, always in the process of becoming something else. The sky itself, the blue we see on cloudless days, is not actually blue, or rather, the blueness is not a property of the sky, but a property of light and air and our eyes. Because air molecules, mostly nitrogen and oxygen, are just the right size to scatter blue light more than other colors. And so when sunlight enters the atmosphere, the blue wavelengths are bounced around in all directions, are dispersed throughout the sky, and wherever we look, we see some of that scattered blue light. And we interpret it as the color of the sky itself, though really we're seeing an effect, a consequence, an interaction between light and matter that creates the appearance of a blue dome, a blue ceiling, when in fact there is no ceiling, no dome, only an increasingly thin atmosphere that gradually gives way to the black of space. And this blue changes throughout the day, is deepest and purest when the sun is highest, when light is traveling through the least amount of atmosphere and becomes paler, more washed out, closer to white toward the horizon, where light must travel through more air, must scatter more completely, and on very clear days in dry climates, the blue can be so dark it's almost purple, almost navy, a blue that feels deep enough to fall into, while on humid days, on hazy days, the blue is pale and soft, almost grey, because water vapor and other particles scatter all colours more equally, creating a whitish haze that dulls the pure blue we expect. Clouds affect this blue, of course, affect the light that reaches them and the light they reflect back to us. And one of the most beautiful interactions between clouds and sky is the phenomenon of crepuscular rays, those beams of light that seem to radiate from the sun when it's low and partially hidden behind clouds, shafts of illumination that spread across the sky like spokes on a wheel, and we call them God rays sometimes, or sunbeams, or Jacob's ladder. And they appear solid, appear three-dimensional, but really they're just the contrast between illuminated air and shadowed air, between the places where sunlight is reaching and the places where clouds are blocking it. And because of perspective, because of the way parallel lines seem to converge as they recede from us, these parallel rays of light appear to radiate outward from a single point, appear to spread and diverge when in fact they're traveling in essentially the same direction, parallel to each other, and it's only our position, our viewpoint, that creates the illusion of radiation, of spreading, of beams reaching out across the sky. Sometimes when conditions are perfect, when the air is calm and the temperature at the ground is colder than the air above it, a layer of fog will form, and fog is simply a cloud that has decided to touch the earth, a cloud that exists at ground level rather than floating above. And to walk through fog is to walk through a cloud, to be inside that collection of suspended droplets, to feel them on your skin, to see the world transformed into soft edges and muted colors, into a place where distance becomes uncertain, where the familiar becomes strange, not frightening exactly, but different, othered, made mysterious simply by the reduction of visibility, by the way the water in the air scatters and absorbs light. Fog forms in valleys before it forms on hilltops, forms over water before it forms over land, follows the cool places, the low places, the places where warm, moist air meets cooler surfaces and gives up its moisture, and on cold mornings in certain landscapes, You can watch the fog like a river, filling the low places, the creek beds and hollows, while the higher ground remains clear. And as the sun rises and warms the air, the fog begins to thin, begins to lift, not rising exactly but evaporating from the bottom up. And you can watch the process, watch the world gradually reveal itself, watch the tops of trees emerging first, then fence posts, then the ground itself. And it happens slowly enough that you can observe it, can see the transition, can witness the moment when the fog decides it's had enough, when the air has warmed sufficiently that the droplets can no longer remain suspended, and they evaporate, return to the invisible, and the fog is gone as if it never was, though of course it was, is still there in fact, just no longer visible, no longer condensed, waiting for the next cold night, the next calm evening, the next opportunity to gather itself and appear again. Some fogs are so thick, so persistent, that they have names, reputations, histories. The Thule fog of California's Central Valley, for instance, which can last for days or weeks in winter, reducing visibility to almost nothing, creating an eerie, muffled world where sounds are dampened and directions become confused, or the fog of the Grand Banks off Newfoundland, where cold Labrador current water meets warm Gulf Stream air and creates nearly constant fog, a hazard to ships for centuries, a presence so reliable that it became part of the identity of that place, part of what it means to be there, to navigate there, to live there. And then there are morning mists, which are thinner than fog, more delicate, more temporary, evaporating within minutes of sunrise. And these form when the ground has radiated away its heat overnight and cooled below the dew point, and moisture from the air condenses on every surface, on grass blades and leaves and spider webs, and some of that moisture remains suspended in the air just above the ground, creating a layer of mist that might be only a few feet deep, that you could step over if you wanted to, that exists in that thin boundary between earth and atmosphere, between solid and air. And to see this mist at dawn, lit from the side by horizontal sunlight, is to see something that feels ancient, primordial, like the morning of the first day, like the beginning of things, though of course it's not the beginning, is simply another repetition of a pattern that has repeated itself billions of times, that will repeat itself billions more, indifferent to our observation, our appreciation, our presence or absence. Clouds, like fog, can form from water or from ice, and the distinction matters because water droplets and ice crystals behave differently, fall differently, look different when light passes through them, and in the middle ranges of cloud altitude, where temperatures hover around freezing, clouds often contain both, a mixture of supercooled water droplets which are still liquid even though they're below the freezing point, and ice crystals which form when those droplets finally freeze, often around tiny particles that act as nuclei, as seeds for the ice to grow upon. And these mixed-phase clouds are perhaps more common than pure water clouds or pure ice clouds, and they exist in a state of constant transformation, with droplets freezing and crystals growing, and all of it happening in slow motion from our perspective. Though from the perspective of the droplet, from the perspective of the crystal, the changes are instantaneous, are quantum, are discrete jumps from one state to another with nothing in between. Ice crystals in clouds grow through a process called deposition, where water vapor turns directly into ice without passing through the liquid phase, and the shape the crystal takes depends on temperature and humidity, on the exact conditions in that particular region of that particular cloud at that particular moment. And this is why snowflakes have such varied forms, such intricate patterns, because each one grows in slightly different conditions, takes a slightly different path through the cloud as it forms and falls. And while it's not quite true that no two snowflakes are identical, because at the smallest scales, the simplest forms, there's probably some repetition, it is true that complex snowflakes, the ones with elaborate branching structures, are nearly unique, are individual expressions of the physical laws that govern crystal growth, are examples of how simple rules, applied consistently, can create infinite variation. But snowflakes only form in the coldest clouds, and most clouds are warmer than that, contain only liquid water. And these clouds can still produce rain, but they do it through a different mechanism, through collision and coalescence, where droplets bump into each other and merge, grow larger, and the larger they become, the faster they fall. And the faster they fall, the more droplets they encounter on the way down, and so they grow larger still, and eventually, if they grow large enough, if they become heavy enough to overcome the updrafts that are holding the cloud together, they fall out of the cloud entirely, fall toward the earth as rain. And this process, this gradual accumulation from millions of tiny droplets into fewer, larger drops, is happening in warm clouds all over the world, all time, in tropical regions where freezing levels are very high, in summer storms in temperate zones, in any cloud that is thick enough and contains enough moisture for the droplets to find each other, to merge, to grow. A single raindrop, when it finally falls from a cloud, has been on a journey, has been part of many different forms of water, has been vapor and droplet and rain before, has fallen from previous clouds, has flowed in previous rivers, has been part of previous oceans, because water on Earth is constantly cycling, constantly moving from ocean to atmosphere to land and back again. And the water that falls today as rain is the same water that fell as rain 1 million years ago, the same water that dinosaurs drank, that ancient ferns absorbed, that has been ice and liquid and vapor and ice again in an endless cycle that predates life on Earth and will continue long after life has ended, if it ever does. And there's something both humbling and comforting in that, in the knowledge that we're all sharing the same water, have always been sharing it, will always share it, that the water in your body right now has been in countless other bodies, other forms, other places, and will be in countless more after you're done with it, after you've released it back into the cycle through breath and sweat and all the other ways we return water to the world. And clouds are part of that cycle, are one of the visible stages, are the moment when water pauses between being ocean and being rain, between being liquid in one place and being liquid in another place. And they move, these clouds, they travel, sometimes hundreds or thousands of miles before releasing their moisture. And so they're transporting water, carrying it from one part of the world to another. And this is how deserts downwind of mountains receive any rain at all. Because clouds form over the ocean, drift inland, are forced upward by the mountains, cool as they rise, and release their rain on the windward slopes, and by the time they pass over the crest and descend the other side, they've lost most of their moisture. And the land in the rain shadow, as it's called, receives little precipitation, becomes desert, becomes dry, not because there's no water in the world, but because the mountains have intercepted the clouds, have taken their water before it could travel farther. And this pattern, this rain shadow effect, shapes entire ecosystems, determines what can grow and what can't, what can live and what can't, creates boundaries and transitions that are ultimately drawn by clouds, by the paths they take and the barriers they encounter. The speed at which clouds move depends on the wind speed at their altitude, and winds aloft are often much faster than winds at the surface, can reach hundreds of miles per hour in the jet streams, those rivers of air that flow from west to east in the upper troposphere. And clouds caught in these fast-moving currents can cross an entire continent in a day, can travel from the Pacific to the Atlantic, from the Himalayas to the Pacific, carrying not just water but also dust, pollen, pollution, volcanic ash, whatever particles happen to be suspended in the air at the altitude where they're moving. And so clouds are part of a global transport system, are mixing the atmosphere, distributing materials, connecting distant places through invisible flows that only become visible when conditions allow water to condense, allow clouds to form, allow us to see the currents that are otherwise hidden, otherwise unnoticed. There are clouds that form in the wakes of ships, long linear clouds that stretch for miles behind vessels crossing the ocean, and these ship tracks, as they're called, form because the exhaust from ship engines contains particles that act as cloud condensation nuclei, giving water vapor something to condense onto. And in marine environments where there are plenty of water vapor but relatively few natural particles, these artificial particles can trigger cloud formation that wouldn't have happened otherwise. And from satellites, You can see these ship tracks crisscrossing the oceans, creating patterns that reveal shipping lanes, that show the paths of commerce, that make visible the normally invisible intersection between human activity and atmospheric processes. And scientists study these ship tracks because they're accidental experiments in cloud formation, natural laboratories where one variable has been changed and the results can be observed and measured and compared to the unaltered clouds nearby. There are also clouds that form because of airplane contrails, those white lines that streak across the sky behind high-flying aircraft, and these are different from ship tracks, are made not just from particles but from the water vapor in the jet exhaust itself, which freezes immediately in the cold air of the upper troposphere, forms ice crystals that can persist for minutes or hours depending on the humidity of the surrounding air, and sometimes these contrails spread, widen, merge with other contrails, eventually become indistinguishable from natural cirrus clouds, become part of the cloud deck, and there's some debate about how much these contrails affect climate, affect the amount of sunlight reaching the ground, affect the amount of heat trapped by the atmosphere, and the answer seems to be that they do have an effect, small but measurable, enough to matter when you add up all the flights, all the contrails, all the artificial cirrus clouds created by aviation, but not so large that it dominates the climate system, not so large that it outweighs other factors. Just one more input, one more perturbation, one more way humans are, perhaps inadvertently, affecting the atmosphere we all share and depend on. But whether formed naturally or with human influence, all clouds eventually dissipate, eventually lose their coherence, eventually return to invisible vapor. And they do this through evaporation, through the droplets absorbing heat from the environment and breaking apart into individual water molecules that spread and mix with the surrounding air, becoming part of it, indistinguishable from it. And this happens at the edges of clouds first, which is why clouds often have fuzzy boundaries, soft transitions from visible to invisible, because the edges are always evaporating, always dissolving. And if you watch a small cloud on a calm day, you might see it shrink, see it fade, see it gradually consume itself from the outside in until nothing remains but clear air. And the water that was in that cloud hasn't gone anywhere, hasn't vanished, has simply changed form, changed state, moved from the visible spectrum back into the invisible. And it's still there, still moisture in the air, still available to form another cloud when conditions are right, when temperature and humidity and particle concentration align once more. Some clouds last for seconds, small puffs that form and dissipate almost as soon as you notice them, while others last for days, massive systems that cover thousands of square miles and persist as long as the atmospheric conditions that created them persist. And the longest-lasting clouds are often associated with slow-moving weather systems, with stationary fronts or persistent high-pressure zones, with situations where the atmosphere finds a stable configuration and settles into it, and these clouds become part of the landscape, become the sky you wake up to and go to sleep under, become so constant that you might forget they're there, might stop noticing them, until suddenly one day the pattern breaks, the system moves, the clouds clear, and you remember what blue sky looks like, remember what direct sunlight feels like. Remember that the grey ceiling you'd been living under was never permanent, was always temporary, was always waiting for the right conditions to change. And just as clouds form in layers at different altitudes, so too does the atmosphere itself exist in layers, in strata, each with its own characteristics, its own temperature profile, its own behavior. And clouds can only form in certain layers, can only exist where there's enough moisture and the right pressure and temperature conditions, and this is mostly the troposphere, the lowest layer, where all our weather happens, where temperature generally decreases with altitude, where convection is possible, where air can rise and fall and mix and create the instability that drives cloud formation and precipitation. But sometimes clouds form higher, in the stratosphere, the layer above the troposphere, where temperature actually increases with altitude, where the air is stable and stratified and doesn't mix much. And these polar stratospheric clouds, or nacreous clouds, are rare and beautiful, glowing with iridescent colors when the sun hits them at the right angle. made of ice crystals or sometimes supercooled droplets of sulfuric acid or nitric acid, and they only form in the coldest parts of the winter stratosphere, over polar regions, when temperatures drop below -80 degrees Celsius, and they're so high, 15 to 25 kilometers up, that they catch the sun before it rises and after it sets, glowing in the twilight like mother of pearl, like oil on water, like something not quite of this earth. But most of the time, most clouds are ordinary, are unremarkable, are simply part of the daily spectacle of the sky doing what it does. Water vapor condensing and evaporating, droplets forming and falling, and there's a beauty in this ordinariness, in this constant patient process that has no audience, no observers, that happens whether anyone is watching or not, that continues through the night and through storms and through all the moments when we're looking elsewhere, thinking about other things, living our lives without reference to the slow drama unfolding above us. And yet it's always there, always available, always ready to be noticed if we choose to look up, to pause, to take a moment to observe what's happening in that thin layer of air between us and space, between ground and stars, between the familiar and the infinite. The altitude at which different clouds form tells us something about the state of the atmosphere, about what's happening at different levels, because each altitude has its own temperature, its own humidity, its own wind patterns, and clouds reveal these invisible conditions, make them visible, give them form and substance, and meteorologists use clouds as diagnostic tools, as indicators of atmospheric structure, looking at the types and levels and movements of clouds to understand what the atmosphere is doing, what it's likely to do next. And while modern technology, satellites and radar and computer models, have made weather forecasting much more accurate and less reliant on direct observation, there's still value in simply looking at the sky, in noticing what kinds of clouds are present, how they're moving, how they're changing, because clouds contain information, encode information about processes that are otherwise hidden from us. Sailors have known this for centuries, have developed elaborate systems of cloud observation and interpretation, have sayings and rules and guidelines passed down through generations, like red sky at night, sailors delight, red sky in morning, sailors take warning, which is actually based on real physics, real atmospheric behavior, because in the mid-latitudes, weather systems generally move from west to east, and a red sunset means the western sky is clear, means the approaching air is dry, means fair weather is likely, while a red sunrise means the eastern sky is clear, means the weather has already passed to the east, means clouds and moisture are approaching from the west, and while this rule isn't perfect, isn't always accurate, it works often enough that it's been remembered, been repeated, been found useful by people whose lives and livelihoods depended on reading the sky correctly. Another old saying, mares' tails and mackerel scales make tall ships take in their sails, refers to cirrus clouds and altocumulus clouds, both of which can indicate approaching storms, approaching instability, because mares' tails, those wispy cirrus clouds, often precede warm fronts, and mackerel scales, those rippled altocumulus patterns, can indicate mid-level instability, and together they suggest that conditions are changing, that the stable fair weather is giving way to something more active, more energetic. And while modern sailors have weather forecasts and radar, the clouds themselves are still telling the same story, still encoding the same information they've always encoded, still available to anyone who learns to read them, who takes the time to notice patterns, to see relationships, to understand that the sky is not just something to look at, but something to learn from. Clouds affect temperature in complex ways, sometimes cooling the earth by reflecting sunlight back to space, sometimes warming it by trapping heat radiated from the surface, and which effect dominates depends on the type of cloud, the time of day, the angle of the sun, the properties of the underlying surface, and scientists who study climate spend enormous amounts of effort trying to understand these effects, trying to quantify them, trying to include them accurately in computer models that simulate the climate system. And it's difficult because clouds are variable, are chaotic, are influenced by processes that operate at scales from millimeters to thousands of kilometers, from seconds to seasons, and capturing all that complexity in a model is challenging, perhaps impossible in its entirety. And yet the effort continues because clouds are too important to ignore, too influential to leave out, too significant in their effects on energy and moisture and the entire global system to treat as an afterthought or a simplification. Low, thick clouds like stratus or stratocumulus tend to cool the planet because they're good at reflecting sunlight. They have high albedo, meaning they're bright. They bounce a large percentage of incoming solar radiation back to space before it can be absorbed by the surface. And during the day, this cooling effect is significant, is measurable, is one of the reasons why overcast days are cooler than sunny days, why places with persistent cloud cover tend to have more moderate temperatures, less extreme heat. And from space, from satellites looking down, these low cloud decks appear very bright, appear almost white, appear as features that clearly are reflecting a lot of energy, are preventing that energy from reaching the ground, from warming the ocean or the land, from entering the climate system at the surface level. High, thin clouds like cirrus, on the other hand, tend to warm the planet because while they do reflect some sunlight, they're not very thick, they're not very bright, they're mostly transparent, and so most of the solar radiation passes through them and reaches the ground, but they're very good at trapping infrared radiation emitted by the surface, at preventing that heat from escaping to space, and so they act like a blanket, like insulation, allowing energy in but not allowing it out as easily. And this warming effect can persist through the night, through times when there's no solar input, because the thermal radiation from the surface is happening all the time, day and night, and high clouds are always at least partially opaque to it, always trapping some of it, always warming the atmosphere below them relative to what it would be if the sky were clear. And then there are clouds in the middle ranges, at middle altitudes, and these can have either warming or cooling effects depending on their thickness, their composition, their coverage, and the overall effect of clouds on climate is the sum of all these individual effects, all these local variations, all these momentary interactions between sunlight and water droplets and ice crystals and the surface below. And when you add it all up globally, when you integrate over the entire planet and over time, clouds currently have a net cooling effect. They reflect more sunlight than they trap heat. They lower global temperatures compared to what they would be in a cloudless atmosphere. But this balance is delicate, is sensitive to small changes. And as the climate warms, as the atmosphere changes, the behavior of clouds might change too. The balance might shift. The cooling effect might diminish or the warming effect might increase. And understanding these potential changes, these feedbacks, is one of the major uncertainties in climate science. One of the major challenges in predicting how much and how fast the planet will warm in response to increasing greenhouse gas concentrations. But these are large-scale concerns, global concerns, and tonight we're not trying to solve climate models or predict the future. We're simply observing, simply noticing, simply allowing ourselves to be present with clouds as they are, as they exist in this moment, as they drift and form and dissipate according to processes that are both completely understood and yet somehow still mysterious, still capable of surprising us, still capable of creating formations and effects and combinations that we haven't seen before and may never see again. Sometimes clouds form in waves, in regular patterns that ripple across the sky like waves on water, and these are called gravity waves. Not because they're caused by gravity in the sense of things falling, but because gravity is the restoring force, the force that wants to bring disturbed air back to equilibrium. And when air is pushed upward by some disturbance, by wind flowing over a mountain for instance, or by a thunderstorm updraft, or by any other perturbation, gravity pulls it back down, but the air overshoots, goes too far, and then gets pushed back up again. And this creates an oscillation, a wave, that propagates through the atmosphere, and if conditions are right, if the humidity is right at the wave crests, clouds will form at each peak, creating a regular pattern of cloud bands separated by clear air, and these patterns can extend for hundreds of miles, can be visible from satellites as regular stripes across the landscape, as ripples in the otherwise smooth flow of the atmosphere. Lenticular clouds are a special case of this wave phenomenon, forming when wind flows over mountains and creates standing waves on the downwind side. Waves that don't move but remain stationary relative to the ground even as air flows through them. And at the crest of these waves, where the air is coldest, where humidity condenses most readily, smooth lens-shaped clouds form, and they appear to hover in place, appear to be stationary even though the wind is blowing hard, even though air is rushing through them constantly. And this is because the clouds aren't things, aren't objects, but processes. Locations where condensation exceeds evaporation, where water becomes visible, and as air flows into the wave crest, it cools and forms cloud, and as it flows out the other side, it warms and the cloud evaporates. And so the cloud appears stationary even though its substance is constantly being replaced, constantly flowing through. And lenticular clouds can stack up in layers, multiple lens-shaped formations floating at different altitudes, each one marking a wave crest, each one smooth and elegant and unlike any other cloud type, often mistaken for flying saucers or other unidentified flying objects because their shape is so unusual, so perfectly defined, so seemingly artificial. The air inside a cloud is not calm, is not still, is full of motion, of turbulence, of updrafts and downdrafts and eddies and swirls, and the droplets that make up the cloud are being carried along these currents, rising and falling, circulating. And this motion is part of what keeps them suspended, keeps them from falling immediately to the ground, because the updrafts can be strong enough to overcome the settling velocity of small droplets, can keep them aloft indefinitely as long as the convection continues, as long as energy is being pumped into the system from below. And it's only when droplets grow large enough, heavy enough, that they overcome the updrafts and fall out of the cloud. And in strong thunderstorms, the updrafts can be so powerful that even large hailstones are carried upward repeatedly, growing a new layer of ice each time they're lifted into the coldest parts of the cloud, until finally they become so heavy that even the strongest updraft can't hold them, and they fall to earth as ice, sometimes ice the size of golf balls or even larger, ice that started as a tiny droplet or a tiny ice crystal, and grew through this violent cycling up and down through the storm cloud's internal circulation. But most clouds are gentler than that, contain motions that are slower, more subtle, more like the lazy turning of water in a pot that's just barely simmering, and these clouds produce drizzle or light rain or no precipitation at all, are simply collections of droplets that drift and gather and slowly change shape and eventually fade, and they're beautiful in their ordinariness, in their lack of drama, in the way they ask nothing of us except perhaps to notice them, to appreciate them, to spend a moment observing the way light filters through them, the way they frame the sun or the moon, the way they create depth in the sky, create a sense of three-dimensionality, of layers and distances and spaces between things. When the sun is low, within about 6 degrees of the horizon, and there are ice crystals in the air or in high cirrus clouds, sometimes a halo appears around the sun, a ring of light at a precise angle, 22 degrees of arc from the center of the sun's disk. And this halo forms because ice crystals act like prisms, bending light, refracting it. And the hexagonal shape of ice crystals means they bend light at particular angles, and the 22-degree angle is one of those special angles, is where the refracted light from millions of ice crystals all happens to converge, creating a bright ring, often with a reddish inner edge and a bluish outer edge, because red light is bent slightly less than blue light, is refracted at a slightly smaller angle. And if you see this halo, you're seeing a demonstration of optics, of geometry, of the regular internal structure of ice crystals all doing the same thing, all bending light in the same way. And the result is this perfect circle in the sky, this ring that follows you as you move because it's defined by an angle from your eye to the sun, not by a fixed location in space. Sometimes, in addition to the halo, sundogs appear, bright spots of light to the left and right of the sun at the same altitude. And these form from plate-shaped ice crystals that are falling through the air and orienting themselves horizontally as they fall, like leaves drifting down. And these horizontal crystals refract light, just like the randomly oriented crystals that create the halo. But because they're all oriented the same way, the light they refract is concentrated in particular directions, creating these bright spots, these mock suns. And on very rare occasions, when conditions are perfect, you can see an entire complex of optical phenomena all at once. Halos and sundogs and tangent arcs and circumzenithal arcs, a whole geometry of light and ice crystals. A display so intricate and beautiful that it seems impossible. Seems like something that shouldn't exist in the natural world. And yet it does. It happens. Following simple optical laws, simple physics, creating something that feels like magic but is actually mathematics, is actually predictable and understandable, and yet still somehow miraculous. These optical effects, these interactions between light and water and ice, are part of what makes clouds endlessly interesting, endlessly variable. Because not only do clouds have different forms and different altitudes and different lifetimes, they also interact with light in different ways, create different colors and effects and phenomena, depending on their composition, their structure, their position relative to the sun or moon. And so the same cloud can look completely different from different angles, at different times of day. Under different lighting conditions, can be grey and flat from one direction and brilliant and colourful from another, can be boring and ordinary one moment and spectacular and memorable the next. And this variability, this context dependence, is part of what makes sky watching so rewarding, because you never know what you're going to see, what combination of conditions will produce what effect, what moment might offer something unexpected, something rare, something worth stopping to observe. In tropical regions near the equator, where the sun is intense and the ocean is warm and evaporation is constant, clouds form through a different process than in temperate regions. Form through intense convection, through the rapid lifting of warm, moist air that rises like bubbles in boiling water. And these clouds can grow enormous, can tower 40 or 50,000 feet into the sky, can create their own weather systems, their own circulation patterns, and they organize themselves into clusters and lines and systems that can be seen from space as massive spirals of white against the blue of the ocean. And these tropical cloud systems are engines of heat transport, are mechanisms for moving thermal energy from the surface where it's absorbed to the upper atmosphere where it can be radiated to space, and they're essential to the global climate system. Are one of the main ways heat is distributed from the equator toward the poles, from the tropics toward the temperate zones. And without them, the planet would be far more stratified, far more extreme in its temperature gradients, far less hospitable to life as we know it. But even in these dramatic tropical systems, even in the most intense thunderstorms and the most powerful hurricanes, the basic process is the same, is water evaporating, vaporizing, droplets condensing, clouds forming. And it's just the scale and intensity that's different, the amount of energy involved, the speed of the processes, the magnitude of the effects. But the fundamental physics, the fundamental chemistry, the fundamental principles are identical. Whether you're talking about a small cumulus cloud on a summer afternoon over Iowa, or a Category 5 hurricane in the Gulf of Mexico, and there's something unifying in that, something that connects all clouds, all weather, all atmospheric processes into a single system, a single interconnected web of cause and effect of energy and moisture and motion. Clouds over the ocean look different than clouds over land because the surface properties are different. Because ocean surfaces are smooth and uniform and dark, absorbing most of the sunlight that hits them, while land surfaces are rough and varied and often lighter in color, reflecting more light. And this affects the temperature of the surface, affects the amount of moisture available for evaporation, affects the stability of the air. And so marine clouds tend to be more stratiform, more layered, more persistent, forming in the stable air over cool ocean waters, while continental clouds tend to be more convective, more varied, responding to the uneven heating of the land surface, the differences between forested areas and open fields, between dry soil and wet soil, between sun-facing slopes and shaded valleys. And clouds over cities form differently too, affected by the heat island effect, The way urban areas are warmer than surrounding rural areas because of all the concrete and asphalt and buildings that absorb heat during the day and release it at night, and affected also by the particles in urban air, the pollution, the smoke, the dust, all providing cloud condensation nuclei, providing seeds for droplets to form around. And so urban clouds can be different in their properties, in their droplet-sized distributions, in their brightness, in their tendency to produce precipitation or to hold on to their moisture. And these differences are subtle, are not obvious to casual observation, but they're real, they're measurable, they're part of the complex interaction between human civilization and atmospheric processes, part of the way we've changed, perhaps inadvertently, the very air we breathe and the clouds that float through it. There are clouds that form from smoke, from forest fires or volcanic eruptions, and these pyrocumulus clouds, as they're called, are created by the intense heat of the fire or eruption creating its own weather system, its own convection, lifting moisture and smoke particles high into the atmosphere where they cool and condense. And sometimes these clouds can grow so large, so energetic, that they produce lightning and thunder, create their own storms, and firefighters watch for these pyrocumulus clouds because they indicate extreme fire behavior, indicate that the fire is generating enough heat to create its own winds, its own circulation, potentially making it even more dangerous and unpredictable. Volcanic eruptions can inject material directly into the stratosphere, above the weather, above the zone where clouds normally form and precipitation normally falls. And this material, this mixture of sulfur dioxide and ash and water vapor, can spread around the entire globe, can create a haze that lasts for months or years, can create spectacular sunsets, can cool the global climate by reflecting sunlight, and the clouds that form from volcanic emissions are different from ordinary clouds, are often thinner, more persistent, more widespread. And they're a reminder that clouds don't only form from the water cycle, from the ordinary processes of evaporation and condensation, but can also form from extraordinary events, from disasters, from moments when the Earth releases energy in sudden, violent ways. But most of the time, the Earth is not erupting, fires are not raging. The atmosphere is simply doing what it does, moving moisture from place to place, from ocean to land and back again. And clouds are part of that circulation, are visible markers of atmospheric rivers, of moisture plumes, of the streams and flows of water vapor that course through the atmosphere like currents in an ocean. And these atmospheric rivers can carry as much water as the Amazon, can transport moisture from the tropics to the mid-latitudes, can fuel winter storms and create flooding when they make landfall. And we're only beginning to understand them, to track them, to predict their behavior, because for most of human history they were invisible, were unknowable, were simply weather happening. And it's only with satellites and modern observation systems that we can see these flows, can watch moisture moving across the planet in real time, can understand that what feels like local weather, like isolated rain, is actually part of a global system, part of flows that span hemispheres and oceans. The highest clouds we've mentioned, the noctilucent clouds, form at the mesopause, at the boundary between the mesosphere and the thermosphere. At altitudes where the atmosphere is so thin it's barely there, where temperatures are the coldest anywhere on Earth, colder than anywhere on the surface, colder even than Antarctica in winter, dropping to minus 120 Celsius or lower. And at these temperatures, the tiny amount of water vapor that makes it to those heights can freeze onto meteoric dust particles, can create ice crystals that catch the light of the sun long after it's set for observers on the ground. And these clouds are increasing, becoming more common, and scientists think this might be related to climate change, to increasing methane in the atmosphere that breaks down at high altitudes to produce water vapor, or to changing circulation patterns that transport more moisture to the upper atmosphere. And so, even at the edge of space, even at altitudes where humans have never gone without spacecraft, the atmosphere is changing, clouds are responding, and the sky we look at tonight is not quite the same sky that people looked at a century ago, will not be quite the same sky that people look at a century from now. But these changes are slow, are gradual, are measured in decades and centuries rather than days and weeks. And on the timescale of a human life, on the timescale of a quiet evening watching clouds drift by, the sky seems eternal, seems unchanging, seems like something we can count on to be there, to be beautiful, to be available for our observation and appreciation whenever we choose to look up. And perhaps that's enough. Perhaps we don't need the sky to be literally eternal, don't need it to be unchanging. We just need it to be there for us, to outlast us, to continue its slow processes long enough that we can return to it again and again throughout our lives and find it familiar, find it comforting, find it still engaged in the same ancient dance of evaporation and condensation, of formation and dissolution that has been its nature since the first oceans formed and the first clouds drifted above them. When you see a cloud, any cloud, you're seeing the end result of countless small events, countless molecular interactions, water molecules breaking free from liquid surfaces, rising through the air, cooling, slowing, colliding with particles, sticking, clustering, forming droplets. And each droplet is itself a collection of billions or trillions of water molecules, all temporarily organized into this form, this structure, all held together by hydrogen bonds, by the weak electrical attractions between molecules. And these bonds are constantly breaking and reforming, constantly allowing the droplet to maintain its shape, while also being flexible, being able to merge with other droplets, being able to evaporate at the edges, being both stable and dynamic at the same time. And the water molecules themselves are ancient, are made of hydrogen atoms that formed in the first moments after the Big Bang and oxygen atoms that formed in the cores of long-dead stars and were scattered through space when those stars exploded, and these atoms drifted through the galaxy for billions of years before coming together in the cloud of gas and dust that collapsed to form our solar system. And they've been part of Earth for 4.5 billion years, have been through countless cycles, have been part of magma and rock and ocean and ice and vapor and living things and dead things and everything in between. And right now, some of them are in a cloud above you, condensed into droplets, visible, observable, temporary, and soon they'll evaporate again, will return to invisibility, will continue their journey through the hydrologic cycle, through the carbon cycle, through all the interlocking cycles that make Earth a living planet, a dynamic planet, a planet where matter flows and circulates and never truly rests. The science of clouds, the study of how they form and evolve and dissipate, is called nephology, from the Greek word for cloud, and it's a science that requires patience, requires observation, requires a willingness to watch and wait and notice patterns, because clouds are not like laboratory experiments, are not controllable, are not reproducible. You cannot make the same cloud twice, cannot isolate variables, cannot hold conditions constant. You can only observe, only record, only try to understand what you're seeing. And this makes nephology as much an art as a science, as much about intuition and experience as about equations and measurements. And the best cloud scientists are often the ones who have spent the most time simply looking at clouds, simply being present with them, simply developing a feel for their behavior, their tendencies, their rhythms. And you don't need to be a scientist to appreciate clouds, to find meaning in them, to let them calm you, to let them slow your thoughts, to let them carry your attention away from whatever has been troubling you and toward something simpler, something more fundamental. Water and air and light, the basic elements of weather, of atmosphere, of the thin envelope of gas that makes life possible on this particular planet, in this particular corner of the universe. And perhaps that's enough of a thought to hold on to as you drift towards sleep. The idea that above you, always, there is this process happening, this gentle transformation of invisible to visible and back again, this patient accumulation and dispersal, this flow that needs nothing from you, asks nothing of you, simply continues, simply persists, simply is. Sometimes clouds form in patterns that seem too perfect, too regular, too organized to be natural. And these cloud streets, as they're called, form when the wind is blowing in a consistent direction and convection is happening in regularly spaced cells, creating rows of clouds aligned with the wind, parallel lines stretching across the sky for miles, and from the ground they might look like furrows in a field, like something planted, like something intentional. But from above, from satellites, they're even more striking, more obviously patterned, more clearly the result of some organizing principle, some regularity in the atmosphere that creates structure where you might expect chaos, creates order where you might expect randomness. And these patterns emerge from the interaction between heating and wind and the rotation of the Earth, from Coriolis effects and boundary layer processes, and all the complex physics that governs how air moves, how it organizes itself, how it responds to forces and gradients and constraints. There are also clouds that form in hexagonal patterns, in honeycomb structures, and these are seen most often in marine stratocumulus decks, where cold air is flowing over warmer water, creating conditions where convection organizes itself into cells. And in each cell, air rises in the center and sinks at the edges, or sometimes the opposite. Air sinks in the center and rises at the edges. And either way, the result is this regular pattern of cloud and clear sky, of covered and uncovered ocean surface. And the pattern is self-organizing, emerges from the system itself without any external template, without any blueprint, simply as the natural consequence of the physical laws operating under these particular conditions. And it's another example of how clouds, how weather, how atmospheric processes in general tend toward patterns, toward structures, toward organization, even in the midst of apparent chaos. The color of a cloud at sunset depends not just on the cloud itself, but on the atmosphere between the cloud and the observer, on the amount of dust and moisture and pollution in the air, on the angle of the light, on the altitude of the sun below the horizon. And this is why tropical sunsets can be so different from desert sunsets, can be so different from mountain sunsets, because each environment has its own atmospheric composition, its own typical particle concentration, its own way of scattering and absorbing and transmitting light, and the clouds, being at the mercy of the light that reaches them, being passive reflectors rather than active light sources, show different colors, different intensities, different gradations, and no two sunsets are ever quite the same, even in the same location, even on consecutive evenings, because the atmosphere is always slightly different, the clouds are always slightly different, the angle is always changing. There is a moment just after the sun has set, when the sky is still bright but the sun itself is hidden, when clouds low on the horizon are already in shadow, but clouds higher up are still catching the last rays of sunlight, still glowing while everything below them darkens. And this creates a layering effect, a sense of depth, a demonstration that the atmosphere has vertical structure, that different altitudes are experiencing different lighting conditions, different moments in the transition from day to night. And if you watch carefully during this time, you can see the shadow of the Earth rising, can see the boundary between illuminated and shadowed atmosphere moving upward, creeping up the sky as the Earth's rotation carries you farther from the sun, farther into night. And the highest clouds are the last to fade, the last to lose their color, the last remnants of day before the sky goes dark and the stars emerge. And then in full darkness, clouds can still be seen if there's a moon, especially a bright moon, a full or nearly full moon, and moonlight is just reflected sunlight, just the sun illuminating the lunar surface, which in turn reflects some of that light back toward Earth. And it's much dimmer than direct sunlight, about 400,000 times dimmer. But it's enough to see by, enough to cast shadows, enough to illuminate clouds, and clouds in moonlight are silver and grey and white, are stripped of colour because the light is too dim for our colour vision to function, because our eyes have two types of receptors, cones that see colour in bright light and rods that see shades of grey in dim light, and in moonlight we're using mostly our rods, mostly our night vision, and so the world becomes monochromatic, becomes a study in brightness and shadow, in light and dark. And clouds in this light have a particular beauty, a quietness, a softness that daylight clouds don't quite possess. Some cultures have special relationships with clouds, have developed elaborate cloud mythologies, cloud deities, cloud symbolism, and in these traditions clouds are often messengers, are carriers of rain and therefore of life, are beings or phenomena worthy of respect, of observation, of gratitude. And this isn't superstition exactly, isn't wrong, because clouds really are carriers of water, really are essential to life, really do determine whether crops grow or fail, whether rivers flow or dry up, whether a place can support human habitation or not. And so paying attention to clouds, learning to read them, developing a relationship with them is actually quite practical, quite grounded in survival, in the needs of agricultural societies, in the realities of living in a world where water comes from the sky and clouds are the visible sign that rain might be coming or might not, and learning to distinguish between clouds that promise rain and clouds that don't was a valuable skill, a necessary skill, a skill that could mean the difference between feast and famine, between continuation and collapse. Modern meteorology has made us less dependent on direct cloud observation, has given us tools and technologies that can predict rain days in advance, can track storms from space, can warn of dangerous weather with enough lead time to take shelter, to evacuate, to prepare, and this is wonderful, is life-saving, is one of the great achievements of modern science, but it's also distanced us from the sky, has made us less attentive to clouds, less aware of their patterns and meanings, and perhaps we've lost something in that trade. Perhaps there's value in the old practice of simply watching, simply noticing, simply being in relationship with the sky above us. Not because we need to predict the weather ourselves anymore, but because there's something inherently meaningful in observation, in attention, in the practice of noticing what's happening around us and above us, and understanding that we're part of it, part of the system, not separate from it, not immune to it, but embedded in it, affected by it, shaped by it in ways we might not even fully recognize. As you lie here in this quiet space with your eyes closed or open, it doesn't matter which. You might imagine clouds, might picture them in your mind, might visualize their slow drift, their gentle transformations. And this act of imagination, this internal visualization, is not so different from actually watching clouds. Because what you see when you watch clouds is already heavily mediated by your brain, is already interpreted, filtered, constructed from the light patterns hitting your retinas and the associations and memories and expectations you bring to the observation. And so imagining clouds and seeing clouds are perhaps not as different as we think, are both mental constructs, both representations, both ways of engaging with the idea of clouds, with the reality of clouds, with the phenomenon of water suspended in air, visible and temporary and beautiful. And whether you're watching real clouds or imagined ones, the effect can be similar. The calming, the slowing, the softening of whatever urgency or anxiety you brought to this moment. Because clouds move at their own pace, change at their own rate, and they cannot be hurried, cannot be rushed, cannot be made to do anything other than what they're already doing. And there's something liberating in that, in surrendering to their rhythm, in accepting that some things just take time, that some processes unfold at their own speed regardless of our wishes or needs or schedules. And maybe this is part of why we find them relaxing, because they model a different way of being, a different relationship with time, one that isn't driven by deadlines or urgency or the constant pressure to do more, be more, accomplish more. The water that makes up today's clouds has been clouds before, has been rain before, has been ocean and river and groundwater and snow and ice and vapor, has cycled through the Earth system countless times, and it will cycle countless times more. And this continuity, this persistence of matter through transformation, is one of the deep patterns of the universe, one of the fundamental truths that science has revealed, that matter is neither created nor destroyed, only transformed, only rearranged, only moved from one form to another in an endless dance that has been going on since the beginning of time and will continue until the end, if there is an end. And in this dance, clouds are one movement, one expression, one temporary arrangement that appears and dissolves and appears again somewhere else. And we get to witness it, get to be present for it, get to observe this ancient process that has been repeating itself since long before humans existed and will continue long after we're gone. And in that perspective, in that cosmic time frame, our own concerns, our own worries, our own troubles while they matter to us, while they're real and valid and deserve attention, are also small, are also temporary, are also just one arrangement of matter and energy that will dissolve and be rearranged into something else. And perhaps that's not a depressing thought, but a freeing one, a reminder that nothing is permanent, that everything changes, that the cloud you're watching will not be there in an hour, will have transformed into something else or nothing visible at all, and so too will your current situation, your current challenge, your current pain or joy or confusion will transform, will give way to something else. And all you can do is be present with what is, right now, in this moment, watching or imagining or simply knowing that above you, the sky continues its processes, the air continues to move, the water continues to cycle, and you are here, breathing, resting, being part of it all. Clouds don't know you're watching, don't care whether you notice them or not, don't perform for an audience, don't exist for your benefit or entertainment, and yet they offer something freely, without conditions, without expectation of return. They offer beauty, offer pattern, offer movement and change and the simple fact of their presence. And you can accept this offering or not, can pay attention or not, can find meaning in it or not, and the clouds will continue regardless. Will drift and form and dissolve according to the physics that governs them, according to the temperature and humidity and wind patterns that shape them. And in this way they're perfect companions for falling asleep, because they ask nothing, require nothing. Simply are, simply exist, simply continue their slow processes while you gradually release your grip on consciousness, while your thoughts slow and scatter and drift like the clouds themselves, formless, weightless, untethered, floating in the space between waking and sleep, between awareness and not awareness, between this moment and the next. And so the clouds drift on, whether you're watching or not, whether you're awake or asleep, whether you remember them in the morning or forget them entirely. They continue, patient, indifferent, beautiful in their indifference, in their lack of concern for anything other than the simple physics of their existence. And perhaps that's the final gift they offer, the reminder that the universe continues its processes regardless of our attention, that there are forces and patterns and systems much larger than us, much older than us, much more persistent than us, and we can rest in that knowledge, can let ourselves be small, be temporary, be just another arrangement of matter that will exist for a while and then dissolve back into the elements, back into the cycle, back into the great flow of energy and matter through time and space. And the clouds, those temporary gatherings of water droplets, those visible manifestations of invisible processes, drift on, patient and eternal in their transience, present and absent at the same time, here and then not here, now and then never, always and never, visible and invisible, real and ephemeral, substantial and insubstantial. And the sky continues, the air moves, the water cycles, the earth turns, the clouds drift, dissolving into the gathering quiet of your breath, into the softness of this moment, into the gentle darkness, into sleep,